All right, so this is the intermediate axis theorem, or the tennis racket theorem, as we did in problem 3 of problem set 10. So first let me set up the problem, and then I'll work through each of the rotations about each of the principal axes and show that the intermediate axis produces some sort of instability. So the problem setup is we've got a rotating rigid body with principal axes E1, E2, and E3. I've drawn this just because I'm going to do a little demonstration with a book that I've taped up. But this, you can see, produces these moments of inertia, unique principal moments of inertia along these rotational axes, where E1, so the rotation about E1, is less than the rotation about E2, which is less than the rotation about E3. The intermediate axis theorem just says that this intermediate axis here, the E2 axis, is the axis that, when rotated about, produces an instability or a twist. Here are your Euler equations, and what we mean by free rotation is the total torque on the system is equal to 0, so it's just an impulse, and you send it into free rotation. No viscous forces, and the initial angular velocity is confined to one axis. For example, if we were rotating about the E3 axis, omega 3 would be much greater than omega 1 and omega 2, which would be nearly 0. Okay, so now we're going to take this same object. Here I just have a book that's taped up that I had drawn here before, and we're going to rotate it about its smallest intermediate axis, or the axis, the principal axis that has the smallest moment of inertia. In this case, in this object, it is rotating about this axis here. So this is E1. So if we consider that with all of the assumptions that we previously had written down, we know that omega 1 is much greater than both omega 2 and omega 3. In that case, omega 2 and omega 3 are very close to 0. They have a very little initial velocity, which makes this first Euler equation, when the torques are all 0, of course, free rotation, this cancels out that term because omega 2 times omega 3 is approximately 0. If that is the case, that means that omega 1 dot is 0, or approximately 0, which implies that omega 1 is constant, or close to constant. If that is the case, that means that we can take these other two equations, solve for just omega 2 dot and omega 3 dot, and clump the remaining terms in terms of all of the constants, which I've called A and B. So you have these moments of inertia terms, which come from the Euler equations, times your constant omega 1 in both scenarios, and in terms of opposing angular velocities. So omega 3 and omega 2, and omega 2 and omega 3. Rearranging this, or taking the second derivative of each of these things, you can see that this times a constant equal to this would produce just omega 2 double dot and omega 3 dot. Well, we know what omega 3 dot is, so we can substitute b omega 2 into the second derivative of this equation. Do that for both of these, and we get these two expressions here. So it doesn't take a lot of math to get to these two expressions, but we know that this is just the form of a simple harmonic oscillator without damping. And so for an oscillator to be stable and oscillate under stable conditions, we can just rearrange this equation to be in general form, and then we know that the term in front of this term is omega squared. So we know that the frequency of oscillation, the natural frequency of oscillation, is the square root of negative AB. Rearranging this, of course, so you pick up the negative on the way over. So if that's the case, we need this to be real in order to be stable. So AB has to be negative to cancel out this negative so we don't end up with an imaginary term. And we can verify that by looking at what A and B are. Remember that I11 is less than I22, which is less than I33, based on kind of how we set up our problem with the intermediate axis being the one that we're trying to find if it's unstable. So inspecting A and B, if omega 1 and all the moments of inertia are positive, which they should be, then you can see that I33 minus a smaller I11, this term is positive. But coming over to here, I11 minus a larger I22, this term is negative. A negative times a positive is equal to a negative. So we need the condition AB equals negative, or less, AB is negative or less than 0, is satisfied. And so, if we twirl this object about its E1 axis, it's stable. You don't pick up any other angular velocity terms in omega 2 or omega 2 or omega 3. Okay, so now we're going to take a very, very, identical approach almost to rotation about the E3 axis, which is the largest moment of inertia principal axis. That would be rotating like so. So in this, it's a very identical approach to the one that we took with E1, so I won't spend that much time on it, but the omega 1 and omega 2 being small go to 0. This makes omega 3 dot equal to 0, which means that it can be inferred to be constant. Setting up the exact same equations with just the different substitutions. We got A and B, we know our stability condition, and we know that this is the general form of the harmonic oscillator. So looking at A and B need to be negative. So we've got I33 minus I11, that's a large thing minus a small thing, that's going to be positive there. I22 minus I33, remember I33 is larger than I22, so this term is negative. Negative times a positive, we achieve our stability condition, and it is stable. So now we're going to rotate about the middle axis, E2. That looks like rotation about the axis where the moment of inertia is in between the smaller moment of inertia, E1 or I1, and the larger I33. So it's the rotation along the principal axis that is kind of in the middle. That's why they call it the intermediate axis theorem. In this case, with this book here, the intermediate axis is along E2, which is rotation like this. And so let's see if we get stability conditions out of this. Almost identical setup again. Just for thoroughness, we'll go through it again. So omega 2 being the much larger than omega 1 and omega 3. Omega 3 and omega 1 being so close to 0 that this term is nearly 0, which means that omega 2 dot is 0, meaning that omega 2 is nearly constant. Then rearranging the other two Euler equations and taking the second derivative, again, we come to this cluster of constants here. Remember that omega 2 is approximately constant. And so we get these two equations here, and we know that our stability condition is that AB needs to be negative. Now let's look at the moments of inertia specifically here and inspect to see if A times B is actually negative. So looking at A, I11 smaller than I22, this produces a negative number here. So this term is negative. I22 minus I33, this is a smaller minus a larger thing, so this term is also negative. A times B, negative times negative, is a positive, meaning that the frequency of oscillation here is part imaginary, leading to an exponential growth and some terms that don't produce stability. So our stability condition is not met, but let's test it out. So rotating along the intermediate axis, we should get some sort of funky twist. And it does. It twists in midair, and that's the intermediate axis for tennis racket theorem.